Everyone, it's Alex B here with a question on buoyancy from chapter 12 of University Physics. So the question tells us that we have a cylindrical buoy which is floating in seawater at some depth, which we're going to call H. And it tells us that a man comes along and he stands on top. And it asks us how much further will the buoy sink? Well, to know how much further it's going to sink, first we're going to have to figure out how far it sinks originally. So we know that there are two forces acting on the buoy. One is the force of gravity, which is pulling it down. But we know that the buoy isn't going anywhere, so there must be another force, which is pushing it back up. And in this case, that is the force of buoyancy, which we're going to call F sub B. Now, we know from Archimedes' principle that the force of buoyancy is equal to the weight of the seawater displaced, so the mass of the seawater times g. And we know that, as usual, the force of gravity, S of g, is just the mass of the buoy, which I'm going to call capital M, again, times the gravitational constant g. Now, to figure out the mass of the seawater displaced, we're going to need to know the density of seawater, which is just a number given to us by the book, and the volume of seawater displaced. Now we know that the buoy is cylindrical, so it's going to push out a cylindrical volume of water. And in particular, we know that the volume of a cylinder is equal to pi times its radius squared times its height, h, where in this case, h is the depth that the cylinder is sinking into the sea and not the entire height of the cylinder. So plugging that into our condition for the buoy not going anywhere, which is a balance of forces, so we want the force of buoyancy to be equal to the force of gravity. Plugging this in, we should find that we have rho sub seawater, the density of seawater, times pi r squared h, which is the volume of seawater displaced, times g, is equal to capital Mg. And here we see that g just cancels out, as often happens, and we're left with an equation for h, the height that the cylinder sinks in, of capital M, the mass of the buoy, divided by the density of seawater times pi r squared. Now, this is the equation for the depth that the cylinder sinks in without anyone on top of it, but the question asks us, how much further does it sink in when an 80-kilogram man stands on top of it? So we see that the only thing that actually changes in this equation, I'll rewrite it here, that way we can see. So before we had the depth is equal to the mass of the buoy divided by the density of seawater times pi r squared. So we see that the only thing that's actually going to change here is the mass, because the mass of the buoy is now going to become heavier when a man stands on top of it. And in particular, the change is just going to be equal to the mass of the man divided by the density of seawater times pi r squared again. And so we actually don't even need to know the mass of the buoy. We just need to know the mass of the man who stands on top of it, and that will tell us how much further it's going to sink in. Now, plugging in numbers that are given to us, we know that the mass of the man is equal to 80 kilograms. We know that the density of seawater given to us in the chapter is 1,030 kilograms per cubic meter. We know that the radius is equal to 0.9 meters, which is the diameter given to us divided by 2. So that's going to give us 0.45 meters. And pi is just a constant, of course, which we always know. So from this, we're going to calculate that delta H is about 0.122 meters. Here I'm using 3 significant figures because the question gave us 3 significant figures for each of the constants. And converting that to more normal units, that's about 12.2 centimeters. So not very far. But that's to be expected given the fact that the buoy has quite a wide diameter and the man actually doesn't weigh that much. Thanks for listening.